So now, there's a lot of times in electronics where you don't want the load setting the current. You want something else setting a current. The load could accept more current, but it's limited. So in this case, we're going to take an op amp right there, and we're going to set a certain amount of current with an op amp. We have a couple of things to keep in mind. So we have a voltage that we want. So we're going to use a trim pot, give that to the non-inverting input right there. The output, when you send the output to the inverting input, does whatever it can to get the non-inverting input voltage the same as the non-inverting input right there. So inverting, non-inverting. And so that means the load is going to, use up some voltage. So to get to the voltage at the inverting input that you set at the non-inverting input, you need a higher voltage at the output. It's going to just self-regulate like that. So if the load needs 2 volts at a certain amount of current, and you set 1 volt at the non-inverting input, the output's going to have to be 3 volts, drops 2 volts for 1 volt across the inverting input, or at the inverting input I should say. Now, the reason we need that voltage for the current is this resistor right here. So remember, the inputs don't let current in or out. This is the current path right there. We got a resistor from the inverting input to ground right there, and therefore there's going to be a current that flows. That current has to come from the output, go through the load, and then go down to ground. So if we set 1 volt at the non-inverting input, then we're going to have 1 volt at the inverting input. Again, if the load needs 2 volts, that'll be 3 volts at the output. We're not too worried about that. It self-regulates by itself. But we got that 1 volt. This is what we're controlling. And if we use a 1000 ohm resistor, again, something we can control, then that 1 volt will give us 1 milliamp of current going through this path right there. So it's also going to go through the load, as long as the load doesn't demand more voltage than what the output can provide. And again, if we get that up to 5 volts, so we set 5 volts, we got 5 volts there again. If we have like a red LED, that's going to drop a couple volts, so we'll need 7 volts at the output. But in any case, we'll have 5 volts across the 1000 ohm resistor right there, about 5 milliamps of current flowing through the circuit right there. And again, we can double the resistance right there. 1 volt give us half a milliamp current, 5 volts 2.5 milliamps of current. So those are the 2 things we can control: the voltage we set at the non-inverting input, and then that resistor right there, as long as we stay within the limits of the op amps. And a 500 ohm resistor, again, will get twice as much current as 1000 ohms. I'm keeping the math easy because that's the quickest way to learn this basic stuff. So 1 volts, 2 milliamps, 5 volts, 10 milliamps, and so on. Now, of course, the op amp LM358 is, first off, it's not a rail-to-rail op amp right there. It's always going to fall short of the 10 volts. But when you got a load, you're providing any current, it gets even farther from 10 volts that it can output. So our limit is maybe going to be like 8 volts, up to probably like 10, maybe 15 milliamps of current. Might even go down more if you exceed that, even by a little bit. I'm guessing. It was a while ago I did the measurements. But this is not really meant to provide a lot of power. There's ways that you can provide more power, but we're going to focus on the current source part of this. So now, here I have the LM358 op amp, and I recommend getting kits like this. This is the smaller kit, but I bought a lot of other integrated circuits. But in any case, has a variety of integrated circuits right there. NE555, again, is one that you commonly use, and that's a pretty cool component too right there. It's a bunch of transistors just on an integrated circuit. But in any case, you use them as like individual transistors, but they're on the same integrated circuit. So we got the LM358 right there, and this kit has the pin layout. Again, I recommend that if you're got like your basic components, get integrated circuits in a kit where it shows like the pin layout. The more info it gives you, the better. So we have 1 op amp on the left side, so number 1 according to some data sheet I looked at, and then number 2 on the right side right there, and that one and that one. For op amps, I don't seem to have a problem leaving the inputs floating. There's other integrated circuits where if you're not using the integrated circuit, you gotta give the inputs a voltage to stabilize things. But the op amps, I haven't found that to be a problem, although I think the datasheet recommends making it a voltage follower connected to ground. So, in any case, we got the number one, that's the one we're going to use. We have to power the integrated circuit. So positive supply to pin 8 right there. Negative supply to pin 4. I already did that. So that provides power. In the schematic here, I showed those power pins being powered right there. That's usually where it is lined up on there. You may not see that at all, but looking at the other voltages involved in the circuit, you can pretty much figure out what voltage you gotta power it with. But you always gotta wire it up even if it's not on the schematic. Now, right now, I have the inverting input below the non-inverting input. So this is extremely important right here. This is very easy to miss. I still think I missed this a number of times. The physical component, the non-inverting input is below the inverting input, and then the output is on top for each one of these right there, both of them. I drew, though, the non-inverting above the inverting, and probably did that because we got all of this going on right there. I wanted to put it down lower, and it's headed to ground right there. Whereas the trim pot, it's not taking up much space on the drawing, so I probably wanted it up higher like that. Makes sense. It's a 10,000 ohm trim pot we're going to use later on. And so therefore I swapped the position on there. You'll see that all the time. You may even see it like pointing down or pointing up. I don't know. Whatever was easiest to draw at the time. So always pay close attention to the physical pin layout versus what's on the schematic. So now we have the trim pot. And I think this is the type of trim pot that are commonly provided. I could be wrong, but in any case, they just have pins like these jumpers and stuff. So they fit into breadboards really well. There's a resistive element. It's rounded in shape, but that doesn't really matter too much. There is one end of each end of the resistive element has a pin. So that is on the two ends of the component right there. Then we have another pin right there. That's a wiper. That slides across the resistive element. What that does is that if you put 10 volts across it and you set the wiper, halfway right there, there's going to be 5,000 ohms of resistance on top, 5,000 ohms of resistance on bottom, and therefore you're going to build up half of the supply voltage at the output right there. I usually like to plug this in where it comes to the jumpers. And I like to put it on the right side because these two jumpers line up kind of nicely right there. And then our output is to the left there, that middle row right there. Or we could, squeeze in back there if we really want to. But in any case, I usually put a jumper and send that over to where I want to plug it in. Because especially if I'm just using one breadboard, I used to set it off to the right there, but I've been trying to make it narrower there. I can plug this in wherever over there, and very simple. So now, when it comes to load, there's all kinds of loads you want to set a current through for whatever reasons. So we're going to stick with the LED though. That's the most basic one. And so we're going to put the long lead, the anode, to the output. I feel like using the one on the right for this video. Usually I use the one on the left right there, but it doesn't matter. So long lead, the anode, to the output. Short lead, the cathode, to the inverting input. And that's because the output has to be more positive in order to light up the LED, because it's headed to ground through a resistor right there. And here's a 1000 ohm resistor. I got it out of the baggie with the 1000 ohm resistors in it. And you can also look at the color code. In fact, I usually verify the color code with the other resistors in the bag to make sure that it's the right value. And now we just need to take our signal that we're going to send, because these inputs don't let current in or out. They just look at voltage. Very important when you're dealing with voltage dividers right there, that they don't have to provide the current, otherwise that throws off the voltage. And that is it. So now we got the power supply, and this is not the first time I filmed the scene. I made a couple mistakes that I want to go. So first off, as I said before, usually I put the load on that left op amp there, wire up the left side op amp instead of the right side, and makes sense why I would do that, because now the trim pot's kind of in the way, but we're just going to keep running with this. And power supply is 5 volts. So I was expecting 5 milliamps of current because that's set about halfway, but it was lower. And I was filming that because I applied the power, didn't realize I had the lower voltage. And that's all I had to do, raise the voltage. So this isn't as accurate as a multimeter and the trim pot. Doesn't look like it's higher than 5 volts. But in any case, there are some things that can give us slightly different numbers than we expect. But in any case, there we go. 0 volts, there is no current flowing. And then if I turn this up to about 1 volt, it'd be about 1 milliamp current. And then, you know, about 5 volts, 5 milliamps current, as we said before. There's an output limit to the op amp, though. We're not going to get to 10 milliamps of current. When I set this up, first off, the LED drops a couple volts. So the most we could get is 8 volts across the 1000 ohm resistor. And then the output probably only gets to like 8 volts, approximately. So we lose a couple with the LED, probably only get about 6 volts approximately, maybe 7 volts across that 1000 ohm resistor for 7 milliamps of current. So now we're going to take multimeter measurements. I got the multimeter there. We're going to take voltage measurements to begin with, and I have these are just jumpers. They're male on both ends, but I squeezed the alligator clip to it. So you know, it's a simple way of crimping it. I just used a pair of pliers to crimp it, but they work pretty well. So yeah, that's it. I clamp it onto the multimeter probe right there, and then I can plug it into the negative supply because that's the black one that's common, and the voltage we're going to see on display is this voltage in relationship to that one. So that's 0 volts. If we get 5 volts across here in relationship to ground, then it'll say 5 volts. So first, let's go. We could squeeze it into the trim pot if we want to measure it there directly. This meter, it's auto ranging. I just have to set it for V for voltage. If there's numbers, set it to a number higher. And then black probe here always goes into COM. Red probe goes into this spot there, unless we're measuring high current, but we're not measuring high current right now. So yeah, we got about 3.2 volts. As I said before, this is a voltage divider. It outputs, there we go, wasn't sure where I put the screwdriver. It can't provide much current, but it will output, you know, whatever fraction of the supply voltage you got there. So let's go back to our example of 5 volts, about halfway. So I can really fine tune it to, you know, pretty well to 5 volts there. There's multi-turn trim pots if you really need to try to get a precision voltage. But we're not going to worry about that too much. So yeah, we got that that 5 volts. That's our non-inverting input, the bottom one. So I can go down there, and may differ slightly due to resistance, but for the most part, looks like it's the exact same voltage. So that's going to go across the 1000 ohm resistor as well, right there, the same voltage. So there we can see that. That's the inverting input, though that's not the output. We have the red LED, so it's going to be about 7 volts approximately. The trim pot will do whatever voltage is needed. That's one nice thing about these current sources, to cover that voltage difference of the LED right there. So we got that 5 volts, plus it looks like about 1.86 volts. It does go down a little bit at lower currents, you know, below 2 volts. But here we'll measure across the LED directly, about 1.9 volts across the LED. So now we're going to measure current. We're going to keep it at the 5 milliamps of current, our 5 volt setting at least, right there. So very important that we're not connected to anything when we set this to measure current. The meter does not limit current, and therefore if you accidentally put it across a voltage source, too much current is going to flow. Although I did limit the current to 20 milliamps from this power supply. So, you know, it'll only be 20 milliamps current even if I went to the output, and this should shut off because it sees a short circuit. But in any case, one important thing we got to do is open the circuit where we're going to measure it. So I'm going to take the 1K resistor, move it up there. Of course, now no current is flowing, and the LED is off. And we're going to be careful, make sure I go to the right spot. So we're going to the inverting input right there, and now we can go to the resistor. So we're bridging the gap. The current has to go through the meter in order to read the current. And there you can see it is pretty close to spot on 5 milliamps of current. So now, earlier I said that if you double the resistance, so we're going to make this 2,000 ohms of resistance by putting another 1K resistor in series with the one that we had before. So again, I'm going to be careful that, well, first I'll set the meter to measure milliamps of current, and then I'll be careful. So I was careful to make sure that the probes weren't connected to anything electrical right there. And so going to go to where the LED and the inverting input are, and then we're going to come, so we're going to get both resistors right there. Current's going to have to go through the two of them before it goes to ground, and there you can see we got about 2.5 milliamps of current instead of 5. Pretty straightforward. And then if I just bypass that one resistor, so we go back to the lone resistor, then we got 5 milliamps of current. Pretty straightforward. So I'm going to pluck that one, and we can also look at 500 ohms. So I do have a 510 ohm resistor. That's close enough. I don't have a 2000 ohm resistor. I have 2200 ohm resistor. So this is a really easy way to overcome those resistance differences if they're an issue. Just take 1K resistors, put them in series or parallel. So this is parallel. So now each resistor is connected to that jumper there, you know, going through the multimeter right there. And then each resistor is also connected to ground right there. So half the current's going through one resistor, half the current's going through the other resistor. They're both 5 milliamps of current, but both of those currents also have to go through the meter and the LED, you know, everything else right there. So yeah, we got 10 milliamps of current right there. So for a current source like this, if you have a certain amount of voltage coming in, but you want twice as much, you know, certain amount of voltage set, I should say, but you want twice as much current, then you can just, you know, put the same amount of resistance in series. That's one of your options there if they're fixed resistors right there. You could also use a variable resistor to make it variable as well. This could be wired as a variable resistor instead. You could just have the wiper going to ground, get rid of that positive one, not for where it is now, but you could use that up there. But in any case, we're going to move on. So now we're going to go back to looking at the output limitations of the LM358. So we should have about 10 milliamps of current flowing through there. And by the way, I should have unplugged everything before I turned off the multimeter, turned it off of milliamps. But I forgot actually. I started turning the dial and I realized it was still having current flowing through it when I did that. But probably didn't damage anything. But it's a good idea, especially measuring current. Get it so no current's flowing through it as soon as possible when you're done measuring, because blowing the fuse is the easiest thing you can do to cause damage, and you just got to replace the fuse. Not a huge deal, but it is a pain. So there we got 5 volts, as we said before, at the output, and that's going to lead to 5 volts at the non-inverting input, because that's a direct connection right there. But then the op amp's going to do what it can to give you 5 volts at the inverting input, and to do so, it has to take that voltage plus whatever the load needs right there. So we got 7 volts. But now we will be able to turn the trim pot to 10 volts, and we can measure that as well. But the output with the 10 milliamps current looks like it's limited to 8.2 volts. So this is going to be about 6.2 approximate. You know, it may vary a little bit at the inverting input. That's not the same as the non-inverting input, the plus right there. So we're given about 10 volts with the trim pot, but we hit that limit of the output right there, about 8.2 volts. And we can do a couple other things. So one thing we can do is that's with 10 milliamps of current. Let's check with 5. There you can see it went up a little bit more. It can provide a little bit more voltage because it doesn't need to provide as much current. And now we got the output voltage with no load, which is probably pretty close to what it's going to be when we got so that's to the positive supply. That's the problem. There we go. Put it to the negative supply, and I accidentally, okay, it did go to the negative supply. There we go. So this is about 5 milliamps of current. We got about 2,000 ohms of resistance because they're in series. So looks like 10 milliamps of current. It can still get close to the maximum voltage it can provide. But even with no load, not having to provide current, it's not giving us that full 10 volts of the supply. That's something you always got to be aware of with the outputs. They have limitations. And again, even without a load, this doesn't go to the positive supply. Some can go all the way to the positive supply and the negative supply, but not when they have to deliver current. They might fall like a volt short or something. So you always got to learn the limitations of the output and work within those limitations.